given to people in the conference, and all of them had this mysterious process and nobody knew what the function was except one person. And the challenge to the attendee from the conference was to figure out the function by the end of the conference. And the challenge that I set to you guys was to figure out the function in 2 days, looking at all the data. So, before you, I hope some of you looked at it. Can someone tell me what's the label for Peyton Manning according to the full data?
Over like on the second row maybe. We'll have to take this entire setup over there on the second row. Right now?
Oh.
I mean, it's not visible at all. You see?
Okay, I should use light blue then. Okay.
It's not visible through the camera.
That's very far, so you keep the camera there. Yeah, maybe from there. We're learning as we go along. So we are learning this as we go along. This is a kind of reinforcement learning. You learn, you make a mistake, and things get better. If the colors are not visible, or if you can't read something, just tell me and I'll read it out to you. But you said Peyton Manning is plus.
Have to take it somewhere.
What about Eli?
On the second row,
Minus.
maybe on the third row.
Did people say that just because I would have put 1 plus and 1 minus, or is there a
There is an exposing socket down there.
Okay. So how are the labels generated?
So what should we do for this?
Okay. Any other suggestions?
Let's see if
Any other suggestions for the name? For the label? Okay. Okay, so I'm going to take that answer. In fact, it's a good answer because I even put it on the slide. To the best of my knowledge, this is the function that was used to generate the data. The second letter of the first name is the vowel, plus as it's a minus. I hope those of you who looked at the data agree with this.
Yeah.
Okay. So there was a discussion on the on Canvas as well, I noticed. So, and someone wrote a program to check it, so very cool. But I have some questions. How do you know you're right?
I called both of them. It's a group call. It's a group call.
So, in the last lecture, there was a suggestion that said there's a function that fits these 6 examples, something about the last character of the first name. Right? It fits these 6 examples as well. So, an important question that you should think about when it comes to machine learning is, if I hypothesize that the function is producing the label, producing some value, and this function is derived from training data, what's the guarantee that this is the right function? I first generated that data, and I'm hoping none of you emailed them. So the only person who knows the correct answer was him. So, and this is really the fundamental question that we'll keep coming to. Anytime you suppose you invent a learning algorithm, you should ask yourself, how do I know that this learning algorithm is doing the right thing?
That's how. Yeah, sure.
Speaking of learning algorithms, what learning algorithms should you use? How do you get to that function?
So stop and the last two.
You give me an answer, so I'll
So
ask you
it
first.
will ask you, do you want to extract the broadcast?
Which function?
So select yes.
Yeah.
Then it will ask you, do you want to say yes or no? Select to
Okay,
save.
so
Yes, because that will save the entire
Okay.
broadcast.
that's
into
one
it.
position.
So don't save
I
that.
found 4
The video
names
will go
and two
automatically
of
saved.
each share the same last name. So I took the last name out and they were some discrepancy in the positive and negative, and then turned out
So
that
you actually went through a methodical, somewhat methodical process, which is more than I ever did with this data, which is I looked hard at the problem and wrote down the answer. But how do you arrive at a function is what we expect learning algorithms to do. So I encourage you to think about that. Think about the process that you went through. So is it running, the video?
Yes.
Oh, okay. And is someone there?
No.
Okay. So I encourage you to think about the process that you went through to generate that function. It could be something methodical by ruling out things. And there are other issues related to learning. How do you know that you have to look at the letters? Why not the number of characters? Why not the weight of the person? Why not the day of the week? How do you know that the letters are where the information is? Or how do you know the second letter is where the information is? So this is something that we'll look at quite a bit, and in fact even today. It's about features. Isn't it just modeling data? Or where is the prediction here? Are we just not taking a data set and summarizing it? What's the difference between summary, statistics, and machine learning? There are a few differences. One of them is that in machine learning, we are trying to predict values for unseen examples, like Eli Manning. Now, most of you, when I said the function involves the second character and checks if it's a vowel, nobody asked me what's the vowel. You just have background knowledge. I don't know how you know what's the vowel. I'm pretty sure none of you went to my grade school. And we seem to agree. This is another important aspect. We need to bring in background knowledge. Mostly because without background knowledge, we have no hope for learning. And I'll show you a toy example later today, which actually proves that without actually, in complete ignorance, learning is impossible. Computationally impossible. And the other question is about what is learning? Or in particular, the setting that I gave you was supervised learning. I gave you examples, one shot. And that was the only interaction you had with the person who generated the data, through the example. So this is a setting for supervised learning. So let's talk about what supervised learning is. But before that, any general questions about, yes?
You said without complete ignorance, learning is impossible. So how learning started?
That's a mildly philosophical question. And I'm going to defer answering that mostly with the point of, I'm going to say that let's wait till the end of at least this lecture or towards the end of the semester to get back to that. At the end of this lecture, I'm going to tell you that you need to make effectively some sort of a guess about the function space. About you think the answer involves the character and vowels and such things. You know that vowels are properties of characters. So how does it start? I don't know. And I don't want to make any claims about it because I'm not an expert on that, on learning from scratch. So, but that's a good question to keep in mind because it's often very interesting to think about trying to learn with as little assumptions as possible. Especially when you want to prove things about learning. When you want to prove things, it's best to think of something called the agnostic setting, where I don't know anything about anything, and can I prove it? And we'll see something about agnostic learning somewhere in the middle of the semester. So let's talk about the basic setting for supervised learning. There are things called instances and labels. These are sets. The instance space is a set of examples, And these are things that you want to classify or predict on. So the instance space could be the set of all emails or the set of all images, or in the largest case, the set of all names. In fact, it's not really a set of names, it's a set of all pairs of words. And there's another set called the label space, and the label space is simply a set of all labels. The classification in the label space is of, at least in the simple cases, the label space is tiny. It's just has two elements, positive or negative, spam or not spam. That's binary classification. And what we want is to find a function that I'm going to call the target function. And this function takes examples from the instance space and produces labels. And as a general word about notation, almost entirely in the semester and also even in the machine learning literature, instances or examples are represented by X and the labels are represented by Y. So there is a target function and I want to find it. I don't know what the target function is. It's hidden from me. And the goal of learning is simply to find this target function. Okay? You guys wanted to find the function that generated the badges data. So effectively, you can think of learning as search over functions. Functions also form sets. And learning is simply search over that set that most agrees with your training data. Is that okay? Any questions about that? Okay. In supervised learning is a subcategory of this class of problems. In supervised learning, the learning algorithm is effectively the algorithm that searches over the space of functions. In supervised learning, the learning algorithm sees examples of that function being applied. So there is something called a training set, which has elements from the instance space, X, and their corresponding labels, f of X. And you are given a finite set of it. Okay? So you have a finite set of labeled examples. And they go into the learning algorithm. Oh well. I'm going to stand here. So they go to the learning algorithm and out comes a model, a learned model. And there is often some abuse of notation, but with respect to the word model, but at least for now, when I say model, I mean the function that is learned, that is produced by this learning algorithm. And the job of this function is to mimic f. This is the standard setting for supervised learning. Now, can you think of other training protocols? Can you? Yes?
Something that samples part of the training data and then resamples it. So it's kind of recursive.
Where's the recursion here?
Or not recursive, it's just, I don't know, in a loop. Like-
Where's the loop here? I'm sorry, I didn't get.
So just take a subset of the training data,
Okay,
train on that.
okay.
So you get a model out, but then you can repeat the process and somehow refine the model based on taking different subsets.
That's one method. We saw, yes.
Just having a way to check if your model is appropriately taking the training data, so having some kind of check system that the model didn't do.
But that could be inside that blue purple box. So
What is it? Was this cross verification?
cross validation.
Cross
Sort of. Actually, I spoke about other training protocols in the previous lecture. At least the very popular ones. Yes.
Like active learning?
Active learning is one, and that's kind of something that you hinted at, where there is a loop, there's a feedback loop. Active learning, just to remind people, is a setting where this set doesn't exist. Instead, the learning algorithm directly gets access to F. The learning algorithm can go to F and say, here's an X, here's an input. What do you think is the label for this? And then it refines its model. And then it says, I've learned something about the function, about the model, about the target function. Now, here's another X. I'm very uncertain about this piece of, this part of the instance space. Tell me the label for that. And this is iterative process. That is like you guys asking me questions and me answering them. Another protocol, which is way more popular than even active learning, is unsupervised learning. Unsupervised learning simply says, you're given the instance space, learn. And clearly, again, that's hard. That's probably harder than supervised learning. But it has some attractive properties in the sense that very often getting labeled training data is expensive, both computationally and monetarily. But for most of the class, we'll be talking about supervised learning, at least for the first 2/3 of this semester. Once you've finished learning, let's say you finished learning, you have a model. I have G. G could be, for example, this function that says if the second character is a vowel, then it's a plus. In the same questions that I asked before show up. How do you know it's good? And that's really the point of evaluation. Evaluation, you have two functions now. You have a target function, F, and a learned model, G. And the most popular way of evaluating a classifier is to take new examples, take a test example from the instance space, apply both functions to them, and see whether they agree or not. So you apply your badges classifier to a new name, and after you actually apply it, I will tell you whether the label is correct or not before. And if you do that enough number of times on examples that you've never seen before, that you did not use for training, that's a measure of that model being good. And occasionally, I'll use the word, very often I'll use the word model and classifier interchangeably. When I say classifier, I mean the function G. So, here's a question for you. First of all, are there any questions about this setup for evaluation? Does this seem reasonable? Is this cheating in any way?
Do we provide any information about what kind of function it is?
You know nothing about what F is. You have you don't even see F. Your only interaction with F is through this set here. You have no idea what F is. You only know that, like the badges data, you only know examples and their labels. You have no idea what, it could have been a very complicated function. It could have been random. But that, I sense that was not your question.
Yeah. Basically, when we have some amount of data, we are trying to construct a function out of it. That is what we are doing.
Yes, yes.
So, if we have no clue about what sort of function it could be, there was
Hold on to that thought. Hold on to that thought for another 15 minutes. Yes.
So on the badges example, we don't have direct access to F. We just have access to a set that F produced.
Right, the training set.
Right. And so we can't test any new names through
Right.
F with our.
On the badges set, it was not a completely legitimate setup. Mostly because I did not have any test set. Well, I had a test set. I know F, so I can produce 20 new names with labels, and then you can test it with me, which is sort of what we did at the beginning of the class. Well, Eli and Peyton Manning were not in the training set, so you can think of those as test examples. But again, just 2 examples are not enough. Yes.
But that's active learning, right?
No, you already fixed your model. In active learning, you get that information and then you revise your model. Well, not you, the learning algorithm.
Yes.
So active learning would imply that we have access to F, that we can try new names into F, evaluate against G.
Yes.
Okay.
Yes. And G keeps changing through the process. You have access to F in a limited sense. It's possible that you think about the following. Think about the following setup. Suppose your learning algorithm had access to F. And suppose your learning algorithm had infinite access to F. Then there's no point in learning because you have F. So typically there's going to be limited interaction with the teacher. And very often the point of active learning is to, over time, stop interacting with the teacher because the model has become good enough. So here's a question for you guys. So what will happen if you use the test examples to train? Not in active learning, in the for now let's just assume that we are all in the supervised regime unless I say otherwise. Can you use test examples to train?
Then what is there for testing?
Okay, that's one problem.
Can you break them up so you have some to train and some to test on?
Sure, that's the usual way in which, that's how things are done. You go out, annotate some data, and then you break them up. You put the test data into a locker, never see it till your training is done, and then pull out the data and test it. That is the right, that's scientifically the right thing to do. Because otherwise you'll have no way of knowing whether your model is good or not. But there's actually a more fundamental problem with using test examples during training. Yes?
Oh, you can just create a giant dictionary.
Exactly.
Memorize it.
Right. Why can't you just memorize? If you had access to the entire test set beforehand, you can just put them in a big table. You don't even have to bother learning. Well, effectively you can think of that also as a model. Your big table is a model. Because it's a function where you can do lookups. It's a pretty brittle model because it never generalizes, and that's why it's really not learning.
Is it like overfitting?
It's overfitting tremendously. Yes. Okay. So good. So let me just summarize and present the same material in a slightly different way. The general setting for supervised learning is there is an unknown function f, and you're given access to a training set where you see f being applied to instances, to inputs, examples, equivalent names. Now, typically the input is represented in something called the feature space. So we saw the instance space, we saw the label space. Inputs are represented in something called a feature space. And the feature space is actually a vector space. And we'll see how that vector space is built in just a minute. But just to recap, given an input example, x, f of x is the label associated with it. G of x is a predicted label. And depending on the nature of f, you have different names associated with problems. If f, or depending on the nature of actually y. If the label space has 2 elements in it, we call it binary classification. If it has k elements in it, it's multi-class classification. If the label space is the set of reals, then you call it regression. And I'm hoping you've at least seen these names before at some point. At least classification, the name classification. Maybe not in machine learning, just as an English word. But binary classification, and in general, this sort of a setting is actually very commonly used. It's probably the most dominant setup that people use when you say machine learning. And what kind of applications does supervised learning work well in? One application is there is no human expert. Nobody knows how. But we can get examples. So one is, for example, if this shows up the most vivid example of this is in biology. I have DNA sequences and I want to find binding sites, whatever that means. And the human race does not know how to find it. Nobody knows how to find it, except through really hard experiments and guessing and needle in a haystack kind of procedure involving wet labs. So we can create examples of if you guys are okay with it, we'll live with purple for today. Unless someone has very strong objections. Does anyone not like purple? Okay, good. So, if there's no, very often we have problems where no human can solve the problem. But we can create examples of the problem. And we have some insights into how the problem can be solved, we just don't know the function. So it's the problem, that's a setting that's ripe for supervised learning. Another one, which is actually really the AI question, is we know how to, we don't know how we solve the problem, but we actually do it all the time. So, so the AI examples involved are, for example, in object detection in images. When I give you a photograph of a cat and ask you to find its tail, you can do it pretty well if the tail is good. Now I ask you how you did it. You would say there's a tail. It's not, you can't explain how you did it, but we know how we can do it easily. So these kind of cognitive tasks are also interesting settings for supervised learning because we can easily generate data. It's not easy, we can generate labeled data. You are the function f in this case. Another setup, yes?
Well, you said there's also a way in which humans are themselves are optimized for recognizing cats.
Oh, sure. Yeah.
Because
yeah.
the ones who can't recognize cats need like cats. So.
Sure. Well, okay, that's
okay, it's kind of tangential. But.
Yes, but that's a valid point. I'll take your point. The other kind of setup where supervised learning is useful is where the desired function is very hard to obtain in closed form, but we can actually get signal for it in a delayed form or eventually. Like the classic example is stock market. I don't know how the stock market works, but if I wait one day, I'll know how it did. So I can always get delayed signal. So I can collect training data and maybe train a model. Once again, we'll be looking at binary classification for most of this semester, so I'm going to just remind you of examples of binary classification. All of you are familiar with spam detectors, I hope. If not, you are in for a very pleasant surprise. It says the spam detector is just a function, a model, G, that says, is an email spam or not? Recommendation systems can be framed as binary classification that goes over every movie or every product on Amazon and says, will this person like this movie or camera or whatever? Or so it's a binary decision. Another growing application for binary classification is detection of malicious software on, say, for example, app stores and such places. And again, time series prediction and so on. So there are many, many, many examples of supervised learning. And what I would encourage you to do is to think about what are the instance spaces and labels. Well, label space in all of this is plus minus. Spam, not spam, or just. I know what to do now. So label space is always binary. The instance space, it's useful for you to think about what the instance space is. Okay, so let's get some more technical meat into this. Let's talk about how we can use supervised learning, or what are the questions that you need to answer for yourself when you're designing a supervised learner. First one is you have to say, what's the instance space? Or basically, what's the example? If you don't know what you're classifying, you're not going to classify it. But that's the more subtle question there is, what are the features? How do what part of the examples should I look at to be able to classify the example? The other question is, what's the label space? Or in other words, effectively, what is the learning task? What are you learning? Even though the label space may have the same cardinality for spam detection and for recommendation, whether you like the movie or not, they have the same two elements, let's say plus and minus. A plus in spam detection means the email is spam. A plus in recommendation engine means you like the movie. And you cannot take a recommendation engine just because it's a classifier and apply it for spam detection. So you need to know what's the task. By saying what's the label space, I mean what's the learning task. Another question is, this is a new concept, what's the hypothesis space? And for now I'll say this about hypothesis spaces. A hypothesis space is simply the search space that your learning algorithm operates on. It's a set of functions that you will search to find your answer. It's a set of functions that the learning algorithm has access to. I've been talking about learning algorithm. Well, it's probably a good thing to ask, what is the learning algorithm? And thankfully, that part of machine learning is somewhat well studied. So there are many learning algorithms out there. And finally, the last bit is actually really important, and it goes into a little bit into the step 4 as well, which is, what is the loss function? Or another way of asking the same question is, what is the evaluation metric? Another way of asking the question is, what is success? What is success for your model? What is success for learning? And being able to mathematically write down the loss function leads to some of the more popularly used, directly leads to some of the more popularly used learning algorithms. I'm going to go over each of these in a little bit more detail. In fact, my plan today is to just go over the first 3 and spend the rest of the semester on the last 2. Let's talk about the instance space. X. This is the picture we had. There was an instance space, there's a target function that takes instances to labels. It's a set. And identifying the correct instance space is very important. By that, I specifically am talking about identifying the correct feature representation. Not so much the inputs to your learning problem. The inputs to the learning problem are defined by your end task. If I have to classify emails, the input is an email. But what I mean by saying, talking about the instance spaces, specifically feature function. Identifying the feature function is really important for any measure of success. And the way we do that is take every element in this space and map it deterministically, very often deterministically, to another space, a vector space called the feature space. And there are two kinds of features, or a few. Primarily, there are two kinds of features. Boolean features are things like, does this email contain the word free or not? Probably a strong indicator of spam. Or they could be numeric. What's the height of this person? What's the length of this word? What was the temperature yesterday? What was the stock price? And so on. Let's try to brainstorm some features for the badges game. You guys solved the badges game. So what could be feature functions that you might have considered? And yes?
How many letters?
How many letters are in the name? So just to clarify, a feature function is a function that takes an example and either produces a number or a boolean. How many letters is a function that takes the name and produces a number. Anything else? Yes?
I tried to add the ASCII values of the letters in certain ways and look at parity. Those weren't good
Okay,
features.
that's an interesting feature function.
Is the second letter vowel?
Is the second letter of a, that's a very good feature function. And I don't know how you came up with that. Yes?
First name, male or female.
First name, male or female. So basically, feature functions are functions that look at instances, examples, and extract properties from them. Okay? If you were a old AI person, you might have used the word sensors here. You have an agent, and the feature functions are the sensors that the agent uses to sense the word. Or another word that is more commonly used, also commonly used, is attributes. What are the attributes of the input? And by that I don't mean random attributes, I mean attributes that you think, as the designer of the learning system, what are the attributes that you think are relevant to the task. Now, as I said, feature functions operate on inputs and produce a boolean or a scalar. And typically what you do is you don't just come up with one feature function, because usually most of the time you don't know what's the good feature representation. You just throw in anything that you can think of into the learning algorithm and hope the learning algorithm figures it out. So typically what you do is you come up with a whole list of feature functions. Is the first letter of all, is the second letter of all, is the third letter of all. And you stack them up. But remember, these are functions. They take, each of them takes an input and produces a boolean or a scalar. When you stack them all up, you get a vector of booleans or scalars. Right? And that's what we call the feature vector. A feature function is simply a template that can be used to produce a feature vector. And every dimension in the feature vector is called a feature. If you've ever had the fun experience of playing on Kaggle or any of these things, you typically get feature vectors. They don't tell you what the feature functions are. You get these large list of numbers, spam or not spam. Another list of numbers, spam or not spam. And that's the interface that most machine learning algorithms operate on. From a geometric perspective, and this is often very important to think about, I just want to remind you that a vector is a point in the vector space. It's a point in n-dimensional space. I can't draw n-dimensional spaces, so I just have drawn 2 dimensions. So every example through these functions gets mapped into an n-dimensional space. How do you visualize n-dimensional spaces?
Matrix.
Project this lower dimensional space.
Actually, that was not a real question. I shouldn't have waited for for an answer. The reason is, it's actually an old mathematician joke. How do you visualize an n-dimensional space?
Matrix.
You visualize an n-1 dimensional space and add one more. And by recursion, you can do 2. So you just use that. The point is, I have no idea how to visualize n-dimensional spaces. Once it comes to n-dimensional spaces, it's probably easier to stick to algebra. But it's also important to know that there is a geometric interpretation here, because very often the geometric interpretation helps you come up with interpretations for the classifier. It lets you define learning algorithms in terms of distances in the feature space. It lets you use concepts from geometry. A little bit more about feature vectors. I told you that feature functions can be thought of as templates that produce feature vectors, and here's an instantiation of that. What's the second letter of the name? So this function looks at the second letter, and if it's an A, it puts a 1 in the first space position and a 0 everywhere else. If it's a B, it puts a 1 in the second position and a 0 everywhere else, and so on. Okay? So this is how I take a function that is, what is the second letter is not a boolean. It's not a number. How do I take something that's categorical, like a character, and convert it to a vector? What you do is you assign a different dimension for every category. So here, the first dimension corresponds to A, the second one corresponds to B, and so on. What will be the length of this feature vector for any example? 26. Basically, one position in the vector for every letter. And by definition, by construction, this feature function will not produce any vectors that have. In fact, every vector produced by this function will have exactly 1, 1 and all zeros, by definition. And this is how you deal with feature functions that are neither Boolean nor numeric. Questions about it? And feel free to interrupt and ask me questions. Yes?
So the representation there is an array. I don't know if this is just for the slides, but does it really matter if you use the array or if you use the ASCII value of it or
The ASCII
number or
Yeah, why not encode your category?
Are you guys asking the same question?
yes,
Basically, yes.
Here's an encode. This is an encoding.
Oh yeah, sure. More efficient ones, and we like efficiency.
Do we really like efficiency? The problem with efficient encodings is it may not be the right representation to learn from. For example, suppose I want a function that says the second letter of the name is a vowel. Suppose that is the classifier. In this encoding, it's very easy to write that function down. It's basically the first one and the one corresponding to E, the one corresponding to I. Basically, I should say it's a function that says these 5 things should be, one of these 5 should be 1. In a more efficient encoding, it becomes problematic. You see that? So, I'm not saying that efficient encodings are bad. In fact, one of the really fun ways of doing multi-class classification exactly follows up on that idea. And in fact, it says instead of efficient encodings, let's think of error correcting encodings and error correcting output codes and things like that. So let's encode labels in other ways. But here we are talking about encoding features, but the same idea applies. Other questions?
I've sort of seen this a little in other places, but sometimes people will use like just a other as a part of your feature vector. So maybe you're expecting 26 letters, but instead you got a period.
Sure, that's a practical issue. You may have to do those kinds of things. Another way of dealing with that is every time you see a new character, you just increase the dimensionality of the vector. every time you see a character that you've never encountered before, you make all your vectors one long. Because you're just starting with zeros.
Is there, is this sort of, I guess, what I was trying to say, I guess more like, do you think, typically do we lean towards maybe one bin for outliers or just an expanding vector, or does it just depend?
It depends. It really depends what you're trying to do. But the point I want to make is good features are important. I want to drill this point. I've said this a few times, but I want to say this, make sure that you get this point. Good features are really important for any hope for success. There are way too many ways of inventing bad feature vectors, feature functions. An example here is, this is kind of a silly example. For the badges game, is there a day of the week that begins with the first letter of the first name? How do you know that's not relevant? I'm guessing none of you considered that function. But I don't know why. And a lot of effort in the application side of things goes into designing feature vectors or feature functions. And some very cool research has become prominent of late, which talks about learning these feature functions. Feature functions are also functions. So why can't I learn them? Yes?
I think using such a feature vector, we have one theory like Occam's razor, and it says that you don't go to
This violates, does not violate, but it's not the simple explanation. Good point, and that's something that will come up quite a bit. This preference for simpler models and simpler features and simpler explanations is something that's at the heart of machine learning. Through this class, I'm not going to tell you much about specifics of how to design feature functions for a particular task. I'll talk about, occasionally I'll talk about general principles for what makes for good features, often from the mathematical perspective. But really, feature function definition is something that you pick up by actually knowing about your domain and doing things. Yes?
Does it make them an art?
Sort of. It is a bit of an art. It is also a scientific question in the sense that when I talk about this part, can I learn the feature functions? The best feature representation for this task is the one that helps me best classify it.
So again, you can just say, how can I know, how can I feature it?
Yes. There is there's a story about the earth standing on turtles, and how do you know where is that turtle standing? Or something like that. There's some old story about it. In any case, so that's about so we've seen things about the instance space. Let's talk about the label space. The label space is actually the target that is the output of the target function, or it's the set that's the output of the target function. And there's not much to say about it right now, except I just want to reiterate this general thing about names of problems change when your label space becomes different. When your label space is Boolean, or when your label space has a cardinality 2, we call it classification. When it has a cardinality k for some text k, it's multi-class. When the label space is a set of all graphs, it's called structured prediction. We will talk quite a bit about binary classification. I'm hoping we'll have time to talk about multi-class classification at some point in the semester. And there's a completely different class that talks about structured prediction. And most of this class will be on these kinds of classification problems, where the label space is categorical. It's a discrete set. The label space can also be event. Regression is when y is set or subset of labels. Ranking is when the labels are ordinal, e.g. labels have an ordering within them. A label of, in Yelp, for example, if a 5-star label is only slightly different from a 4-star label compared to a 1-star. Meaning there's a natural order among the labels. There are only 5 labels, so it is like multi-class, but there's an order. And that could be used, the fact that your output has is ordinal can be used by learning algorithms. But
very
oh, well, I said those words. Okay. Yes, thank you. I'll fix it. Oh, that's the other thing I wanted to mention. I encourage you to spot mistakes in the slides. I guarantee there will be mistakes in the slides. Yes. In fact, here's an example of a mistake. So just tell me if there are mistakes. So there's not much to say about labels, but let's talk about hypothesis. In the 20 minutes that are left, let's talk about a set of functions that we need to search over. And now this is where the thing becomes more interesting. Just to remind you, we have instances which are the sets of inputs. We have labels which are a set of outputs. There is a target function that takes instances to the labels. And the goal of learning is to find this function. It's a search for functions. And this makes this, because it's a search for functions, we have to define a search space. So let's play another game where I'm going to try to convince you, contrary to everything that I will say after this, that machine learning is impossible. Some of you might have seen this example before, so I encourage others to answer me how. Let's say I give you, there is a function. This function operates only on 4 inputs, x1, x2, x3, x4, and all of them are Boolean. I give you a training set. Okay? Now, the question to you is, this is the training set. What's the function? Yes.
It's a Boolean function, basically x3 and x4, or x4 and x1.
Nice. That fits the data. Yes. But
how do we know that there is a function?
how do we know that? Good question.
You said there was one.
Really? There's no one function that fits this data. There are 16 possible entries in this truth table. I have shown you only 7 of them. Right? There are 16 entries, meaning just y can be seen as a 16-dimensional bit vector. 16-element bit vector. How many every assignment to that bit vector is a different Boolean function. Agreed? Now, if there are 16 outputs, there are 2 power 16 possible functions. Right? There are 2 power 16 possible ways in which you can fill up this last column. I have fixed 7 bits. How many functions are left that agree with all the elements here? Many is a good answer. Does anyone say 1? Yes. So, problem with coming up with, what was the function that you said? I'm not trying to pick on you, you're the only one who answered, so I'm going to take that as an example.
x3 and x4, or x4 and x1.
Let's say you're a learning algorithm and you give me that function. I am the owner of the hidden function f, and at evaluation time, I know that you've given me that function, but I'm also adversarial. So I will run that function on all the missing elements of this vector and flip all those bits. I'm allowed to do that because I haven't told you anything. You can't, there's nothing, you can only hold me up to the examples that are annotated, that are labeled. So that means all those examples will disagree with that one function. But I'm going to then give you one example, one of those, and then make you play this thing again. And then you'll give me another function, and I'll make sure that all the other bits don't agree with that other function that you're giving. Effectively, if the teacher is adversarial, learning is impossible because every time the learner makes a guess of a function, the adversarial teacher will change the function. And still have enough room, because there are 2 power 16 functions, still have enough room to make that change. At the very end, let's say I give you 15 of these rows. You find the function that agrees with all but one. Sorry, with all examples, all 15 examples. And you're thinking, most of the examples, my function should be right, but there are 2 functions that agree with all examples, because there is still one more bit of uncertainty. Does that make sense? Anyone has questions about this? So, I have a question. How could we ever possibly hope to learn anything if basically the only way learning is possible is if you see every possible example, every possible element of the instance label?
My function is still right almost half the time.
Well, it's wrong half the time. So,
Good enough.
well, that's one way of. In fact, that's basically an approximation of the answer. Yes.
Well, you're not adversarial, so that tries to change everything. So the other instances are fixed somehow.
But you don't know anything about how they are fixed. Think of the setting of.
Well, I think in that case, a guess is enough. I mean, yes, there are, for example, in this possible set, there are 2 to the power 9 functions that can generate things, so that's enough. I mean, you don't need to do more.
What if the point is, yeah, you can say that I don't need to do more. What if I demand that you do more? Because that's the definition that's the setting that we are operating on. The learning algorithm is supposed to produce one function, not a set of functions.
What if we say our function will produce this much error? Like we give the amount of error that our function will give, and based on that we can evaluate many functions.
Okay. Let me ask you another question. I see many hands up, but let me ask you another question. With 4 bits, there are 2 power 16 possible functions. In many tasks, like say natural language processing, this is, by the way, the length of the feature vector. The number of feature vector is 4-dimensional here. Many tasks like natural language processing, in natural language processing, the feature vector is roughly 1,000,000 dimensions. In 1,000,000 dimensional Boolean space, how many functions are there?
Too many.
Can you?
2 to the 1.
Exactly. Because it's 2, the number of elements in the truth table is 2 power 1,000,000, and the number of different assignments to that column is 2 power 1,000,000. Here it's 2 power 4. So If learning is a search problem and your search space has 2 to the million entries, it's not just a question of accuracy, it's a computationally hopeless task. Now ask me your questions. Yes.
So then, I mean, the way you define it, yeah, if we have a million features, then we get the 2 to a million vector or constant.
2 to the million.
Yeah. But that's implying, I guess what I'm saying is, do we really need the perfect vector every time, or can we get the one that we're only looking at a subspace of those that works most of the time, like in classical physics where we say we looked at all the data and they came up with a solution set for that that said
So
we have these
I
equations.
think you are actually heading to the right answer, but I want you to refine that statement. What do you mean by saying, okay, remember that the search is over functions, not over examples.
I still think that having an approximate solution or approximate function is good enough, as long as we know how close we need to.
Right, but the question is about the computational problem. How do you even search over that space?
What if we reduce the search?
Right. That's the answer. But you had a hand up.
So I was thinking that in case of logical solutions, we have something like K-maps and we can do don't care and reduce.
Sure.
So
Yeah. That's in this specific case that would work. Yes.
Yes,
But effectively, the K-maps and don't cares say that you don't care about things that are the values that are missing. But the setting in learning is you don't care about the values that are available. You only care about the future predictions. Remember that learning is about predicting future examples. So you actually care only about this. And if you make the wrong assumption, you might be terribly wrong. You had a hand.
You can calculate or approximate feature entropy with respect to the desired values and use that to eliminate massive numbers of features.
Oh, that's a cool idea. What I'm going to talk about is a much simpler, a much broader solution strategy, and I'm going to go ahead in the interest of time because there are only 10 minutes. Unless you have something.
I have sort of a philosophical question. So, because when we say that the learning is by some metric that we're improving our score somehow, so as long as we're improving in respect to that, you don't have to get everything right. And we also learn that that's important as well.
Sure.
Right.
I think many of you are actually touching on what is on the next slide, which is you don't have to be always right, and maybe you can restrict your search space. If there are 2 power a million functions to search, who said your learning algorithm has to cover all of them? The most extreme case, if you use something like the K-map or something, you basically cover one of them, the one that agrees. But you could cover a subset of it. You could define subsets of your search space and say that I'm going to, my learning algorithm, only look at how well those the functions in that search space are doing and pick the best according to some definition. At least for the next few lectures, by best I mean consistent, the one that agrees with all your data. Now, for Boolean functions, there are many ways of defining restricted search spaces. I could say that my search space will be the set of all conjunctions, only conjunctions of my literals, simple conjunctions, or just disjunctions, or something called M of n rules. If I have a million variables, a priori I'm going to pick n of them, let's say 20 of them. And M of n rule says at least m of those n should be true for me to say yes. Everything else is false. It's just first place. This does not represent all Boolean functions. Conjunctive normal forms and disjunctive normal forms represent all Boolean functions, but conjunctions are are a strict subset. Disjunctions are a strict subset. One subset of these functions that we've looked at quite a bit are called linear functions, and they are the basis of linear classifiers, and linear classifiers represent all these functions that I have listed above. So let me walk through an example of simple conjunctions in the 7 minutes that are left. That's the data set. And by simple conjunction, I mean a function that's just a conjunction without negations. A and B and C are x1, and so one simple conjunction could be y equals 1, y equals x1 and or y equals x3 and x4. Just a simple conjunction. Okay? And my question to you is there a simple conjunction that explains all this data? By the way, I just want to point out that even single features are simple conjunctions. Just y equals x1 is a conjunction. A conjunction with one element. How many simple conjunctions are there? The answers on the slide. So that's a question basically saying, are you awake? Well done. Why are there 16 conjunctions? In fact, if there are only 16, why bother trying to think too hard? We can just write them all down. So here's my learning algorithm. I'm going to write down all 16 simple conjunctions and see if they agree with my data. So this is a conjunction x1, and this element is a counterexample. When the input is 1, 1, 1, 0, the function that says y equals x1 will say 1. Right? So we can cross out this row. x2, I have another counterexample. x3 has a counterexample. At least all of these have counterexamples. There's also a trivial conjunction which says instead of being 0, or y equals 0 all the time. Basically an empty set. Y is always 0. All of them, at least there are 2 counterexamples of that. So we can rule out these 8 simple conjunctions. There are 8 more, and I'm not going to walk through all of this. It turns out for every conjunction, and I very strongly encourage you to work through this exercise and list them down, convince yourself that this slide is correct. Every simple conjunction that in this list has at least one counterexample from the training set. So I've restricted my search space from 2 power 16 to just 16. Good job, because I can fit everything on a slide. But the bad news is it's too small a search space. There's nothing in this space that explains all the data. Our hypothesis space is too small. Questions?
So is it better to allocate your search space at the very beginning to be a smaller amount, and if it's not in there to continue to increase?
That's a great question. I think as a rough approximation, the answer is yes. There is theory, we will actually see some theorems later on that prove that smaller search spaces are better. Smaller search spaces, if you can find a simple conjunction that agrees with these examples, it will generalize better. It has better generalization properties. If you find an example in a small subset, a function in a small subset that agrees with your data, it is most probably a better model. By the way, each of this, just to go back to notation that I used earlier, each row here is a different model. Every element of the hypothesis space is a model. Okay, so this is also again basically the answer to your question as well. How do you pick a hypothesis space? First cut, you just guess. Something or somebody tells me that this data comes from a certain hypothesis. This function, the target function, lives in this hypothesis space. I hope it lives in that hypothesis space because that's what I'm going to search for. What if it's too small? And that's where this is a question that leads to some very interesting learning outcomes, where you, instead of saying that the hypothesis space, there should be an element in the hypothesis space that agrees with every row. So the point you raised, what if I'm willing to live with approximately correct I pick a hypothesis space, I stick to it, but I only give you the one that is most correct. Another strategy is to develop flexible hypothesis spaces, something that you mentioned. Coming up with a hypothesis space that can shrink and grow as you need. And we'll see examples of both of these eventually. I'm going to wind up because there's only 1 minute left, but here's another hypothesis space called the M of n rule. It says you fix a set of n variables, n can be in this case 1, 2, 3 or 4, and the functions in that space are of the following nature. You fix an n, fix an m. So something like at least 2 of these 3 variables should be 1 for my y to be 1. And as an exercise, and we will go through this again in the next lecture, as an exercise, I want you to see if you can come up with a consistent hypothesis in this space. Using the same learning algorithm, which is list out all hypotheses. So the first question that you should ask yourself is, how many of those are there? Can I fit those on a slide? I did not, so actually try it out. So let me wind up with just a summary about learning about what we learned today. You can think of learning as the removal of remaining uncertainty. I have an unknown function and I want to eliminate uncertainty about the function by pruning the hypothesis space, by picking a function that best agrees with my training data. I don't know what the function is, so I'm trying to use the training data to figure it out. And learning requires coming up with good and small hypothesis space. It could be wrong, but there are strategies to deal with that. So that's the end of today's lecture. If there are any questions, I'm around. If not, I will see you. There's no lecture no class on Monday because it's MLK Day, I think. So I'll see you next